Let us understand about high performance thin layer chromatography. So you should remember about the principle of thin layer chromatography, and the same principle is retained for HPTLC also, but the mechanism of interaction for the retention of the solute or for the retardation of the solute is going to be adsorption here. In most of the HPTLC techniques, the stationary phase material going to be used will be normally silica. As you know, silica is SiO2. It is having SiOH groups. They are called as silanol groups. These silanol groups will become responsible for the adsorption process to be taken place when the solute molecules are more polar in nature and they have the affinity towards the silica. Therefore, the main principle involved for the separation is similar to TLC, but principally the adsorption process is expected. We can improvise the TLC procedures by upgrading to HPTLC technique, especially for the feeding of the mobile phase, application of the sample, and detection of the solutes directly. So we can hyphenate, we can associate any detector, we can connect any detector to the TLC instrument. Therefore, all those solutes which have been stored separated can be directly detected by means of a typical detector. That is done in HPTLC, high pressure thin layer chromatography or high performance thin layer chromatography. Some fundamental differences you can make out between TLC and HPTLC. Very importantly, particle size. Particle size will be 10 to 12 micrometer in TLC, conventional TLC. Very less particle size of the stationary phase is seen in HPTLC, that to 5 to 6 micrometer. And the particles are distributed from 5 to 20 micrometer in TLC and 4 to 8 micrometer only in HPTLC. The film thickness, stationary phase layer thickness will be 250 micrometer in TLC, but in HPTLC it is only 200 micrometer. Plate height will be 30 micrometer, here 12 micrometer. Separation time up to 200 minutes, up to only 20 minutes. Sample volume, only 5 microliter maximum, 0.5 microliter maximum. So the aim is to increase the selectivity of the separation, to increase the sensitivity, to increase the efficiency of the plate, to increase the resolution, to reduce the analytical time, to make the lower volumes of the mobile phase consumption, and possibility for analyzing multiple samples in minimal time. And the procedure is going to be simplified because sample preparation will be in only single step, because we will be using only a single time the prepared sample. So simplified sample preparation due to single use of stationary phase, it is an advantage of this HPTLC, because the detector is going to be connected directly. So solutes are going to be detected soon after their separation is over. So efficient data acquisition and processing is possible while using this HPTLC technique. So in this HPTLC, we can utilize the pressure, we can apply the pressure so that the mobile phase can be forced faster by applying the pressure by means of a slit and an object, mainly plastic sheet, which is covered over the stationary phase present on the TLC plate. A slit will be present. The slit will be present over a plastic sheet that is covered over the stationary phase, and that slit will be connected to a pump. Pump is switched on, pressure is created. By means of the pressure created, the movement of the mobile phase will become faster. So that will take solutes along with that at a faster velocity. Therefore, the analytical time will be reduced. Not only analytical time is reduced, mobile phase is forced very fast. As a result, we can expect the separation efficiency, resolution, and TLC efficiency very high. The efficiency of the separation, resolution of the separation, and the separation efficiency overall will become very high. Analytical time will be reduced by almost 10 times. As I told you, 20 minutes is the time required to complete the separation by HPTLC. 200 minutes is going to be the time required to complete the separation by conventional TLC technique. So 50 microliter to 0.5 microliter mobile phase volume, parallel analysis, so like this. And even in HPTLC, both ways of separation can be done by using polar stationary phase as well as modified stationary phase. Normal phase or reverse phase stationary phases can be used in order to initiate the separation so that the separation can be completed more compatible. So detectors, what are the detectors we will be employing while performing separation by TLC, that too by HPTLC? More commonly, we will use densitometric detectors. Densitometric detectors. Do remember, either single beam or double beam densitometric detectors are used. These densitometric detectors will be functioning in two ways, either reflectance methodology or absorption methodology. The single beam, double beam, reflectance or absorption densitometers are used as detectors in HPTLC. The functioning of these detectors are in two ways, either in reflectance mode or in absorption mode. What is this reflectance mode and what is this absorption mode? Okay, you have a adsorbent, means the stationary phase, and the solute spot. You have adsorbent and the solute spot. You will pass a beam of light radiation through the plate, So the intensity at the overall adsorbent and the spot will not be same. If there is a solute in the spot, the intensity of the incident beam will be definitely differing when compared to intensity of the incident beam at the adsorbent, overall adsorbent. So the deflection between the adsorbent and the spot will be measured by using the reflectance method. So in this reflectance method, we will scan the adsorbent and the spot by moving a beam of light radiation. So the reflectance is going to be measured. Therefore, the area of the peak obtained in the chromatogram, as I showed in the chromatogram, the area is directly proportional to the concentration or the amount of the solute. The area under the peak, the area under the curve is directly proportional to the concentration or the quantity of the solute. This met the principle of reflectance method. Similarly, the absorption method is also going to be measured. You know the difference between absorption and transmission. Any organic compound is having the capability to absorb the light radiation, either UV region or visible region. If there is more conjugation, that will absorb the light radiation belongs to visible region if it is colored. If it is colorless, it will absorb the light radiation from the UV region. So what is the amount of the light absorbed that will be measured in absorption method? So absorption detectors, absorption densitometric detectors will be functioning in such a way that the light transmitted through the plate is going to be measured. Transmitted or absorbed. What is the amount of the light absorbed? That is also going to be measured in these absorption methods. So while using these densitometric detectors, the relative standard deviations are going to be better than 5%, means 5% or less, or else the value will be expected, means these detectors are going to function highly precisely. High precision can be expected because very dilute solutions we will prepare, 0.01%, even that can be decreased to 1 into 10 power minus 3%. Very dilute solution is more than enough to complete the separation process. So the limitation of Beer-Lambert's law is not holds good here. Concentration is directly proportional to absorption while using absorption method. Since we are using dilute solutions, not too much diluted, so the limitation of Beer-Lambert's law is eliminated. Therefore, the precision will be acceptable, highly satisfied. So with this acceptable precision, these detectors are directly used either for the characterization and quantification of the solutes. Let us move on to the applications of thin layer chromatographic technique. As I told you, and summing up the application of TLC, it is employed for both qualitative as well as quantitative analysis. TLC can be employed for qualitative as well as quantitative analysis. In qualitative analysis, the solutes are going to be identified simply by matching the RF values. You can calculate the RF values if you are following TLC, conventional TLC technique, or by using the relative positioning of the chromatogram. If you have used reflectance densitometer or absorption densitometer as a detector in HPTLC, the relative positioning of the chromatographic peak for the standard as well as the solute in the sample, you can compare. What is the relative positioning of the peak for the standard? What is the relative positioning of the solute from the sample? If the relative positioning are the same, means the time TR are the same for both standard as well as solute from the sample, then you can assure that solute is matching with the standard. So you can confirm this solute may be present in the sample. Or qualitative analysis can be done by subjecting the TLC spots what you have obtained by scraping by means of razor blade or spatula. After dissolution of them in a suitable solvent, you can subject it for either spectroscopic or LCMS techniques. You can characterize what kind of solutes present in those samples. You can characterize very easily. So only two ways, either by matching the RF values or by positioning identification between standard and solute in the sample, or by using spectroscopic techniques or liquid chromatography mass spectrometric techniques, you can characterize the solutes present in the sample. Quantitative analysis is also reliable by TLC. So number one is by comparing the area of the spot with that of the standard. What is the area of the spot over the TLC plate? With respect to concentration, the area is spread. If area is more, the concentration is more. If area is less, concentration is less. Or the amount is more or amount is less with respect to greater or smaller areas of the spot. And the scanning densitometer can be employed to measure either the fluorescence or absorption from the spot. If a fluorescent material is used over the surface of the stationary phase, what is the intensity of the fluorescent radiation after quenching is directly proportional to the amount of the substance which is present over that particular spot. You can measure what is the amount. And even by scraping the spot from the plate, extracting the analyte from the stationary phase solid, measuring the analyte by means of a suitable physical or chemical method. Even you can use titrometric method, you can use UV method, you can use visible spectrophotometric method, you can use high performance liquid chromatographic technique. Like this, any other analytical techniques can be employed for the quantification of the solutes by thin layer chromatography. So this is how this flowchart is explaining the applications of TLC, and it is applicable for both qualitative and quantitative analysis. Here I have a small video. You can watch how the TLC separation is going to be performed for the separation of two solutes, and how it is confirmed the separation of two solutes by comparing with the standards. So this video is obtained from Capilano University, Department of Chemistry. We must be very acknowledged to them. You can see the components which will be used for the separation of analytes present in a mixture. You can see the containers, you can see the TLC chamber, capillaries, measuring jar, and etc. So you can see here TLC plate. As I told you, plastic or glass or aluminum plates are used. This is going to be the TLC chamber. After the sample introduction, this TLC plate will be immersed into the TLC chamber. After the immersion of the TLC plate, you can see the migration of the solute molecules along with the mobile phase. Then the solutes separated can be identified by any of the described techniques. So let us go stepwise how the separations are going to be performed. This is a TLC plate. This TLC plate is going to be used, made by the paper or already prepared paper here. You create a line by means of a pencil and a scale. This is going to be the imaginary line on which the sample is going to be spotted. You create points by marking with the pencil and label them as A, B, C, and D. You have containers here now. You have containers containing unknown, standard X and standard Y. Standard X and Y are known compounds. But to assure whether standard X and Y are present in this unknown, whether only single compound or both the compounds are present, we have to identify. So what do you have to do? You take a standard. It is an authenticated sample. Take a standard and you take another standard, that is standard Y. Standard Y or compound Y you take. So mixture of standard X and Y or only standard X or only compound Y, we don't know in the unknown. You take standard X. This is standard known compound. You take a capillary and spot a sample drop over lane A. This is lane A. Lane C also. Use lane C also. So lane A and C, standard X has been dropped. Lane A and C, standard X has been dropped. And Y is taken now by means of other capillary, standard Y on lane B. Standard Y on lane B and C. So C is containing standard X and standard Y. The lane C has been spotted with standard X and Y. Lane A is by standard X, lane B is by standard Y. You take the unknown in which you are going to investigate, you applicate that onto lane D. Applicate onto lane D. Now, the sample introduction is over. What do you have to do next? You take the plate by means of forceps. You have to make sure your hands must be very clean. After the introduction of the sample is over, you have 4 different lanes. You must remember what are the lanes containing. Then you take the slide of the TLC plate and you get immerse this TLC plate into the chamber containing the solvent. So you can pour the solvent, which must be suitable for the separation process to be completed. Now you place the plate, TLC plate, into the TLC chamber. It is contained with the solvent. So you have to make sure mobile phase will move upward by capillary action or gravity. Make sure 1/2 or 2/3 of the distance traveled by the mobile phase. You can visualize this by looking at the wetness of the TLC plate. Solvent front is moved 1/2 of the distance of the TLC plate. You remove out, and you make a line. This is used to measure the distance between the imaginary line and the solvent front. After making a line, you take the plate and you expose to the UV chamber where UV light is illuminating. So as I showed in one of my slides, you can see here after exposing the TLC plate, you can see the dark spots of the standards and the samples. So here sample spot, standard spot has been made, sample spot has been made, standard spot has been made, and sample spot has been made. X, X, Y, Y, and unknown. X. You take a pen or a marker or a pencil, you mark out the spot. Under the UV light, this will impart, the spots will be imparting darkness. Otherwise, no. Under the ordinary light, they will not impart. So you have spotted the points now. You have spotted the solute spot. This is going to be very useful. And this spot you are going to scrap, and you can compare. On lane A, X has been introduced. On lane Y, Y has been introduced. X and Y standards have been introduced. Unknown was introduced on lane D. You can compare now here. Only one spot is seen. So this is as same as the distance moved by this particular spot and this particular spot. And these two spots are because of standard X. There is no spot with respect to standard Y. So Y is absent in the unknown. X is present in the unknown. So the distance moved by this particular spot is as same as distance moved by the standard X in the lane A as well as lane C. So RF value can be calculated by using this formula. So RF is equal to distance moved by the solute divided by distance moved by the solvent. This is the solvent front, this is the origin, imaginary line, solute 1 and solute 2. You measure the distance traveled by solute 1, solute 2 and the mobile phase. They have been tabulated here in millimeters. You can concentrate on this table in order to calculate the RF value for X and Y. So by using this particular formula, so suppose 28 centimeter is moved by a compound and 80 millimeter is moved by mobile phase, 28 millimeter by the compound and 80 millimeter by the mobile phase. 0.35 is going to be the RF value. Measurement will be made in this manner by means of a measuring scale and the pencil. You can record the RF values. So RF values are very close to each other, so you can make sure solute X is present. So the RF value of the compounds spotted here is same as the RF value either here or either here. Therefore, we can make sure that the solute X is present in the unknown. You can see here RF value of 0.36 and 0.35. So RF value is very close to each other. Therefore, unknown is containing solute X. So like this, you can identify the solutes in TLC. So you have another video here. It will give you about the visualization by using different reagents. The TLC plate you can see, and after by using TLC plate and drawing an imaginary line, you can make use of this TLC plate for sample introduction. You can just watch this video. I will explain what the visual reagents or development reagents will come. So you have to make sure that you should not touch the TLC plate because the fingerprint is also going to be exposed when you expose the TLC plate into UV chamber. So these are called as lanes. 1, 2, X, Y, A, B, C, D. Like this, you can create lanes. is a capillary, a sample solution. A volatile solvent is used to prepare the solution of the sample. So different solutes have been introduced on these 4 different lanes. So this is containing a solvent, and you have to immerse the TLC plate onto which the solutes have been introduced. You put it in and close the tap. Liquid is moving, the mobile phase moving taken place. You can see. So 1/2 is moved or 2/3 is moved. You can just stop the illusion and you can remove out. Only one colored solute has been spotted here, and all other solutes are colorless. So that's what I am showing this video, how to identify the colorless solutes by using visualizing reagents. So mobile phase has moved appropriate distance. Now it has to be removed out. So make the mobile phase front in order to know the distance moved by the mobile phase. This is exposing to UV chamber. So after exposing to UV chamber, you can see dark spots. One compound is pink in color after subjecting to UV radiation, and some are black in color, some are dark in color. So these are the reagents we can use instead of sulfuric acid or iodine or nonhydrin. You can use permanganate, phosphomolybdate in ethanol. Permanganate has the ability to oxidize the organic compounds. Spot means it is contained with the organic compound. When you initiate the reaction between permanganate and the organic compound, oxidation takes place. As a result of oxidation, you can see here, the pink color has diminished. The diminishing or decrease in the intensity of the purple or pink color is due to oxidation of the organic compound by permanganate. This is an air dryer. So drying the TLC plate. After drying, you can visualize where are the spots exactly. If any substance on the TLC plate that can be oxidized by permanganate, you can see here. Now you see there are 1, 2, 3, 4 compounds. 4 compounds undergone oxidation. See, you can use this to calculate the RF value. This is by using permanganate. That's it. So this is how we can perform the separation by using TLC technique, and TLC will be performed either by conventionally or by HPTLC method. So now one can understand about this TLC that it is a fundamental tool in order to decide which must be the suitable stationary phase and which must be the suitable mobile phase for the separation of the solutes by liquid chromatography. So that's what in synthetic laboratories, organic chemistry laboratories, once any compound or group of compounds are synthesized, they are subjected to TLC separation, and by means of them we are able to follow and we are able to propose the pace of stationary phases or pace of mobile phases for the complete resolved separation of those compounds. So any synthetic chemist is going to perform the separation, he has to reveal the TLC data. So whoever going to use these compounds for their future investigations, they will follow TLC data in developing the HPLC procedures or in developing LCMS procedure, whatever it is. So we can conclude that TLC is a very important technique, and that is the most useful technique not only for the separation of compounds which are present in the sample, but also for the characterization, quantification, provided a suitable detection system is available. And without TLC, the synthetic chemistry laboratories cannot lead the work. That is going to be a fundamental requirement in any laboratory if you go. Otherwise, we cannot deal synthetic work. As an analytical chemist, I can say that we must have appropriate and adequate knowledge about this TLC. Otherwise, he or she will be an incomplete analytical chemist. So you will be understanding about the stationary phase. So what kind of stationary phase is required? That can be decided by the relative movement of the solute. If the solute is moving properly, or the group of solutes are showing proper movement, then we can conclude that this is going to be the suitable stationary phase. Otherwise, we may have to change the stationary phase, or we may have to change the mobile phase. So 50% of the work is done in order to develop the HPLC procedure. So in order to recap, so in TLC, so far we have discussed about the principle of TLC. What are the kinds of stationary phases and mobile phases we will use in TLC? What are the components required for TLC separation? What is the theoretical background of separation by TLC technique? What is retardation factor? What is retention factor? What is efficiency? What is resolution? What is height of a theoretical plate? Now it is associated with the band broadening or zone spreading. All these things we have understood. And we have also understood about the detection systems, particularly under HPTLC. So we will use normally densitometers. They will be functioning in two ways, either by reflectance mode or by absorption mode. In the reflectance mode, the intensity between the adsorbent and the spot will be measured as a reflection. And where in the absorption mode, the transmission of the incident beam will be measured. So by means of the intensity of the differences between the adsorbent and the spot or the transmitted beam, we are able to quantify the solute, what is the amount of the solute present in the sample. So this is going to be the TLC